Welcome everybody back to BST 322. So tonight I'm going to sound like a broken record, but I'm pretty consistent. I'm going to go through some slides with you, and I put these into the week 3 lecture area so you can follow along in the course shell. They're the Zoom class side set, so I'm going to go over those tonight. Go over examples from the assignments. Those will also match the discussion threads, which people are already posting to. So we've got our same format for the discussion questions this week. And then the quiz should be open tonight. Again, the quiz is matching multiple choice true false based upon these slides in the textbook. So it's all the lecture material. Again, I'm not going to have you do a chi-square on the quiz. So that's just going to be on the material. So again, for the quiz, make sure you've got your, yes, from the office, make sure you've got your materials, your textbook open when you take the quiz. Yeah, someone actually thought I was at the office. They're like, I thought with COVID, you guys weren't in the office, but it's just a background. Okay, so here we go. So this week, hopefully will be a little bit easier, maybe not easier, but it'll be a bit of a review because we spent the first week, right, doing our descriptive statistics, and we did cross-tabulation. We just stopped at the chi-square level. We didn't do the test. Tonight, it'll be a bit of a review. We're gonna go over those cross-tabulation tables that we spent working week 1 on. So now we can do them with that nominal level variables, right? Just putting them in categories and getting counts. So tonight we're going to do the test for that, which we talked about last week with hypothesis testing. This course is heavily weighted for chi-square because in medicine, nursing, health sciences, we typically look at chi-square. I'm going to talk about the other non-parametric tests that are in the book that you'll read about, but we're not going to be performing those analyses in this class. We're going to focus for the analyses on the chi-square, but you'll have to know what the other types of tests are. So here goes the review. We are going to calculate a test statistics. We're going to get a new one tonight. Like last week, we did the t-test, which we knew was from Beer. That was exciting. And the f-statistic. The f-statistic is from ANOVA, and that's based upon a different distribution. And again, we're going to take that. We're going to find a test statistic, take the absolute value, because it may be negative if we're on the lower side of the mean for something like the t. And we look and see, right, if that's greater than a critical value, that's in the back of the book, in the little table we have, then we say the null hypothesis is rejected when the result is significant. So we're testing that null hypothesis. And again, significance, this is not an English class, significance here just means we're not getting a queen on the river, right? We've got the results that we see are not due to chance. It's not some fluke that happened in the card game. It could be real for our patients and our subjects. And remember, the p-value is the probability of seeing that level of test statistic or greater in our data set. So it's a probability that the result occurred by chance. We're either going to look it up again, the back of the book, or in our little table. Let me check this one. I'll open up that text and tables. So this one is the one that's in course resources for you, right? So we're looking at these tables, either in the back of the book if you've got one, or on the little PDF or this little cheat Word document I gave to you. And we're going to compare that value to the table value, right? Or we're going to look at the p-value and we're going to compare that to 0.05. So remember, the test statistic, as it gets larger, the p-value gets smaller and vice versa. So these two are related, right? But they're not the same. This we compare to the book. The p-value we compare to 0.05, which we learned last week we made up, right? We lived with 5% chance. And every time we do it, we get evidence. If the result is significant, we reject the null hypothesis and we accept the alternative. We're always testing the null hypothesis. So again, we compare that to 0.05. So last week we did parametric tests, right? The t-test, the f-statistic, the ANOVA. We're looking at the dependent variable is interval ratio. So if you go back to that cheat sheet in the textbook that Dr. Pulit gave us, these are the ones she has in the textbook, right? So we went over the 1 sample, the 2 sample, and notice we're looking at that DV or dependent variable interval ratio. These are the tests we're going to use, right? And then we have to look as to whether they're related or dependent on each other, depending on what type of t-test we deploy or 1 sample t-test. So we're looking at the independent variable and the dependent variable. So last week we did all interval ratio, right? All quantitative stuff. So that's parametric tests. For the non-parametric tests like chi-square, and we're going to do the variables, and so we're going to look at chi-square tonight. So they're measured on a nominal or ordinal scale with no assumption about distribution. This is the non-parametric. We're looking at categories or ordinal variables that just have a scale to them. So we use these particularly when the outcomes, again, are not on the right scale. So anything that's not interval ratio, we can use a non-parametric for, or if the assumptions are violated. So if you have a small sample size, you could put them into categories, whatever you have, because remember, we can take interval ratio variables and we can make categories out of them, right? So we could say cholesterol, if above 220 is high, below 220 is low. And now we've got high and low, two categories. So if sample sizes are small, we could convert that interval ratio data to a category and we can run a non-parametric test. That's the main reasons we use that. So which test we're going to use, we're going to keep going down the cheat sheet here and go to the next page. There's our non-parametric test. So here's your chi-square. The goodness of fit, we're going to skip in this course. Goodness of fit is just with one variable, one set of values that are categories, and we're going to focus on this course on the rest of them. So the chi-square, we have nominal level variables. So like I told you, I keep this little cheat sheet document because I'm always checking, okay, what's my dependent variable? Is it nominal, ordinal? Is it interval ratio? Is it dependent? Are the groups connected? This is a nice table to keep handy just to make sure you're doing the right test. Again, just like we had with the t-test, right, where we had a pair test, we had the dependent test, we had an independent test. Then within the independent test, we had, if the groups are equal and the variances are assumed to be the same, we can use the pooled variances, or we can use the non-pooled. Same thing with these tests. So we're looking at how many groups we have, the types of comparison, whether the groups are independent or dependent, right? Dependent, the easiest one is like the repeated measures. We measure the same subjects over and over, or if the subjects are related somehow. So we have the same type of thing we'll do for this part of the course. And this is a cute little table too, that's sort of the same thing you're seeing over here, but we're going to spend most of our time tonight on chi-square. Nominal level measurements and two groups or three or more groups. So you can have a 2x2 table, 3x5 table. As long as both are nominal measures, nominal groups, you're going to do a chi-square test. If you have a ranking and you have an ordinal measure, then you use these other type of tests. And we'll talk about these as we go on. For chi-square, we're looking at the relationships between these categorical variables, right? We're going to put them in the cross-tabulation table, pivot table for you Excel people, if you're into math and Excel, pivot table or cross-tabulation table, and we're going to compare the differences in the proportions across the groups. This is also known as a Pearson's chi-square test. So with that long intro, go ahead and start guessing from here, A, B, or C, type in, what do you think our null hypothesis is going to be for a chi-square? Is it that the variables are not independent, they're related, A, B, they're independent or unrelated, it's B, or C, they're moderately related? What would our null hypothesis be here for chi-square? Related, unrelated, or moderately related? We're getting a lot of B's. You guys are getting better at this. Yes, B, the variables are independent or unrelated. So if they're independent or unrelated completely, the chi-square value, the test statistic we're going to compute, and we're going to do a little bit of math tonight, but we're going to make the computer do most of it. It should be 0 for two categorical variables that are completely unrelated. And if the chi-squared value is greater than the tabled value, we reject the null hypothesis and the result is significant. So similar to the t-test where we compared something to a population value, the one sample, we're going to see how far away our chi-square gets from 0 as to whether it's significant. What that means is if they're unrelated, right, the proportions across the groups, across our pivot table, across our cross-tabulation table we did in week 1, the proportions should be equal if nothing's going on. But if they start to change and they're related, the proportions are not going to be equal. We're going to see patients surviving the surgery more than they did with some other treatment. So the proportions will change. Like our other tests, we have to have assumptions. Random sampling is another assumption of our chi-square. Each observation is going to be independent So for chi-square, they can't be the same people. They have to be different subjects. That's the foundation of the chi-square. So if they're twins, if you're measuring them twice and they're the same people, you can't use a chi-square. The other assumption is each part of the table, the expected frequency has to be greater than 0. But what's expected frequency? Well, we'll get to that very quickly. So again, the logic is if that null hypothesis is true and nothing's going on, right, then, and the proportions are the same for the groups being prepared, the test then is going to compare the observed frequencies with the expected frequencies. The expected frequencies are what we would expect to see if the null hypothesis is true. So if nothing's going on, that's what we should expect to see. So let's take a simple example from chapter 8. So here we have an experimental control group. That groups are typically independent variables, right? And then this is our outcome, continents, right? Incontinent, not incontinent. So we want to end up in this area, right? We don't want to be incontinent. So for this group, it looks like for the experiment control, either we gave them medication or behavioral therapy, whatever experimental treatment we gave them, it appears that most of our sample is moving to the not incontinent group, right? Those that didn't get the treatment, a little higher on the incontinent, right? Not good. So what we have to look is if we have this change in proportion, so it looks like it worked, we have to test it. Could it be just random fluctuation, right? Is it that queen on the river we started with last week? That's what we're going to do with this test. So what we have to calculate for that is gone over in that chapter. Let me pull up my textbook here. Again, that's got the tables in it. And what we're going to look is calculating, there's our chi-square distribution. It looks really funky, even worse than the F statistic, right? It's all going to be positive and coming away from 0. It depends on how many cells we have in our table. And we calculate it looking at this equation on page 172. This is what the expected frequencies are. So the expected frequency for each cell is going to be the observed frequency for the entire row that it's in times the expected frequency, the observed frequency over the entire column divided by the sample size, right? So here we have 100 subjects in our group. 30 of them were incontinent, 70 were not incontinent. So again, if the null hypothesis is true and nothing's going on, like a broken record, then we would expect to see the expected counts be the same. So for each cell, you're going to take the observed count, right, and the expected count. So the expected count is going to be that equation here, so the row that it's in. So for the first one, we have this one for cell A, right? We're going to have expected count by this equation. So we will do a little bit of math tonight. Oop, it doesn't like my background. I'm going to switch my background. Okay, so back to the camera. It's going to be the row times the column divided by n. So that's what you have here. So it's going to be the 30, because that's the row it's in, times the column total it's in. So there was 50 in both groups. So there's 50 in our experimental group divided by n, which is 100. So for chi-square, we have to calculate these expected frequencies. So again, if nothing's going on, it's going to be that equation. So 30 times 50, probably do this without my calculator, right? 1500 divided by 100. And so for this one, it's going to be 15. Again, that's our expected count. If the null hypothesis is true, that's the proportion we should see in that cell. So we're just doing this equation here to figure out our expected counts. It's no more difficult than that. So again, if the null hypothesis is true, then the observed would equal the expected, and the observed minus the expected would be 0. That's why we compare the chi-square value to 0, right? So again, we're going to look at the sampling distribution of the statistic, which is up here, and we're going to try to figure out how far away we get from 0. Is that by chance, or is it because something is really happening? So again, here's our example. So for each cell, we're going to calculate the observed and expected. And again, we're going to add those all up. So going back to this one, so if nothing was going on, we should have 15 in that group, not 10. So then we just take the 10 minus the 15, there's the observed, the 10 that were there, and minus the 15, square it, divide it by the expected count, and we get 1.67. So then we take that for all the cells, we do that, and the software is going to do that for us normally. add it up, and that gives us our chi-square value. We're going to look at the degrees of freedom. So here's the degrees of freedom. There it is on page 173. It's just R1 minus 1 times the columns minus 1. So for a 2 by 2 table, we have 1 degree of freedom. So then we're going to look at our chi-square table, and I've got that, and that we did the T table, we did the F. There's our chi-square. Page 416, and also in that little cheat sheet that I gave you. So we compare that to 3.84. Our chi-square value we got was 4.46, so the null hypothesis is rejected because our test statistic is greater than our table value. So for incontinence, there's something about the treatment that is statistically significant. It's real here, as far as the numbers go. So when we do these tables, once we look at them, we can do some corrections. Those are also up here in the little tables, and find that. In statistics, if we have a problem with the chi-square analysis, we can do something called a Fischer's exact test. So that can be added on to the test. There's a little button for it in StatCrunch and many programs. A Fischer's exact test just adjusts the value of the chi-square when it runs the test. So that's if the expected counts drop below 5. We do a Fischer's exact test with our chi-square. And then for Yates correction, if they drop below 10, we do what's called a Yates correction. Really what it does is it reduces the value of the chi-square. So again, we're going to avoid those false negative, those type 2 errors. So again, -5 for expected count Fischer, minus less than 10 in those expected counts, and we're going to apply a Yates correction. For magnitude of effect, like we had for the R value, right? The R values for scatter plots, and we'll come back to those next week when we talk about regressions. For magnitude of effects for that, it's called the phi value. So the phi varies from 0 to 1, very close to our R values from our scatter plots and correlation. Again, these are for 2 by 2 tables, and the corrections for Fischer's and Yates are also just for 2 by 2 tables. Once you get above 3 by 2 or 3 by 4 tables, you can't use those corrections. And the Kramer's V is used for larger tables, ones that are greater by like 3 by 2, 2 by 4. And the phi will equal the Kramer's value for a 2 by 2 table. These values will just tell you the strength of the relationship between the chi-square value. More examples. So if we look at, this is from discussion board number 1, which people are already doing. So here's the table done in SPSS. Right, the statistical package for social scientists. And you can see here, this is back to our heparin log placement time. So this was from figure 8.2, but we saw this one before when we did cross-tabulation tables in week 1. So here we have a heparin block placement time. We put in heparin lock at 72 hours and 96 hours, and then we look at the complications. So again, our dependent variable, our outcome, we're interested in is whether or not the patient had a complication. So that goes into our rows, the groups go into the columns. So here is the output for SPSS, and you can tell that the value here, it's often called sig 0.617. The discussion question is going to ask you to do this calculation, and I think StatCrunch does it out to 4 digits. So how do we make sense out of this thing, and what do we know about these expected counts? Because now we've got 10, 10, 40, and 40. Well, it's the same calculation that we do for the first one, right? So we're going to do our expected count. It's going to be the total for the column that it was in times the row. So the row times the column divided by n. So this is what the software, both in SPSS and StatCrunch, is going to do. So for the first one, it's just going to be the row that it's in, so it's 20 times the column. There's 50 in each group divided by n, and we have 100 subjects. So we just take 20 times 50, which I probably should be able to do in my head, right? That's 1,000 divided by 100. We don't need a calculator for that. So that's where they got this value of 10 from. Again, the expected count. The row that it's in, right, times the column that it's in, 20 by times 50 divided by n, which is 100. So we get 10 for our expected count. Isn't math fun? So that's what the software is doing to give us that count for 10. Then we just do the same thing for the next one, but now there's 80 in that row. So it's just going to be 80 times the column, right, which is 50 divided by 100. So 80 times 50, we get 4,000 in our handy dandy calculator. 4,000 divided by 100, and we get the 40. So this is all the math that the software is doing for us. So it's taking all of those values. If we go back to the textbook, this is what it's doing, right? So if you look at that chapter 8, it's going to calculate all of these expected counts, right, that we just did. Then it's going to take the expected count and subtract it from the observed account, and it's going to square them. So that's why the chi-square distribution is all positive, right? It's going to add them up, and that's our test statistic, and we compare that to the value in the back of the book. And as you can see, 0.250, again, we have 1 degree of freedom. R minus 1 times C minus 1 is 1. And if we go back to our book, compare 250 on our chi-square table, zoom down to it, it's much less than our tabled value. So this one is also not significant, and the software calculated it at 0.617. So for the discussion question, you want to see if you can get that value. And remember, to do that, you don't have the 100 or so values in your StatCrunch sheet, right? So let me go to StatCrunch. For the values for when we have the raw data, we would have all of that 100 in our spreadsheet. But we don't, we have the summary data. So for the first discussion question, see if how good you're at getting the summary feature to work. That's going to be your job for discussion question 1. Another example of summary data, going back to the migraine headache one that we did during week 1 to do a table. Remember, we did this one. For now, we did the cross-tabulation table in week 1. Now can we make sense out of the chi-square? Is this surgical intervention, is it statistically significant? Can we tell our patients that this thing is going to work? Is it going to work or not going to work for them? So again, to get that data in, which is what you'll do for discussion question 1, we have to put in the data, right? So remember, we did this one, we have to reconstruct that table for the summary data. So the first column is going to be the dependent variable. So who can type in and remember, what was our dependent variable here? Was it type of surgery they had, or was it the reduction of migraine, the successful outcome? Which is our dependent variable that we're going to put here first? What's our dependent variable for this migraine study? Is it going to be the surgery group or the reduction in migraines? Yeah, reduction, migraines. So we can put that as migraines, or we can call it success. We're going to put that in the first column, yes or no. Again, nominal level variable, it's just categories, right? And then we have our sham and our real. I can't remember if I mixed those before, but it doesn't matter as long as we have them in the independent variable here. So for the sham, we had 26 subjects, 15 had success, and that left us with 11, right? Correct me if I make a mistake here, but real we did was 41 had a success and 49 total, so 8 were a failure, right? They did not have a successful outcome. So for the summary data, again, we're reconstructing the table because we don't have all of the 75 or 77 patients here, right? Subjects here, we just have this. So now we go up to the table, the stat tab, tables, contingency. We don't have the data, we have the summary. So we click on summary. We're going to select our columns here. So we're going to select the sham and the real. And our row variable is going to be the success column. And now we have the row percents, the column percent, the percent of total, and we're going to click on the chi-square, and we can click on contributions to chi-square. We're going to see if we can add those up. And we're going to leave this by default now. This was on, we're going to leave it clicked on and click compute. So we have our table that we got from last time. So again, I would take this and put this into Word. Again, SPSS, remember, does this for us, but we've just got to do a little fixing here. Right, so I'm just going to right click on here and add some cells above, merge these two. So we can call this surgery intervention or type or group. This one's going to be outcome. We can call it successful outcome, reduction in migraines, whatever we want to call it. We just want to make sure we label it to make sure we've got it right. The first one, so these are just our counts. Then this is, the first one's our row percent. So this is percent within outcome. Then percent within our column. So that's percent within type. And then that's our percent of total. So again, a good review from week 1. Now this one is our expected count. And it looks a little funky because our groups are different. And then the last one is contributions to chi-square. Once I got that typed in, I can just copy that down. And then my total column, though, we don't put expected counts or contributions here. I can just delete those and my table's done. So again, that's saving us $120 a month. We can just put this into Word. But again, SPSS does this nicely. That's the only reason to spend all the money, I guess. But we can do this in Word, no problem. There we have. So again, we've got our 15. So just like we had in week 1, we can talk about, well, here's the sham, there's the sham, here's the real surgery. So those that had successful outcome, most of them, 73% got the surgery, and about 27% did better without, right? They got a successful outcome, but they had the sham. So your odds are better having the surgery, but still some people got there. So Taylor's asking, so when you ask us to include the chi-square result, you want us to put the contributions in the cells. You don't have to for the reports. They can get clunky. I would leave them out since we're going to have it anyway. Oh, where did let me go grab that result. So typically when I do tables, I just put this in and I don't put the contributions to chi-square. But for now, we'll just go over them real quick so we can see where we got this number from. Oop, not the p-value, this one. And again, I should have went back in and reduced the sig figs, but we know how to do that, so I'll just keep going. So there's the chi-square value, 6.06, right? So what it did was it did all the calculations, right? So it had calculated all these expected counts, and now they're a little different because there's different cells, right? So again, expected equals the counts that's in the frequency in the row times the cell, the column, divided by n. So here we have, it's going to be 56 times the column, total was 26, divided by n, which is, our total was 75 in this group, right? When we do this math, right, again, so it's the row it's in times the column, divided by the total n, which is 75. And on my Magic TX 30X calculator, I got 19.41. So that's where that funky number comes from. So this one's a little different because the groups are different. We have 26 in the sham and 49 in the real. So we don't have equal groups, so we're going to get some little bit of different numbers here. So what did it do? It took that number, that was the expected count that we got, it subtracted the observed, so nothing's going on, right? We should have only 15 there. So it took that minus that and added up all of those as it went forward. So we have if we look at this first one for the sham, and then for example, for the real, you get all the contributions for chi-square. So let's look at the sham. We have the chi-square and it's doing this calculation, right? It's gonna take the observed minus the expected and square it, and it'll add it up. So it's calculating all of this chi-square ones, right? So the chi-square is going to be equal to the observed minus the affected. So here it's 15 minus the expected, which is, we calculated at 19.41. That's going to give us a negative number, but we're going to square it and divide it by the expected count, 19.41. So there's the math for the chi-square test statistic. 15 minus 19.41 is minus 4.41. Square it, x squared, divided by 19.41. And I get 1.00196. Well, 1, right? So basically it's 1. So then it's, I mean, I don't think you want to watch me do it. That's what it's doing for each cell. And that's how we got to the 6.06. And Taylor's asking, so every time the expected count doesn't match the observed, we reject the null, correct? Good question. No, if it doesn't match, just like with the one sample t-test, we have to see how different it is from that value. So we're going to see how different this is from 0. And how we tell that is we're going to go back to the table. So that chi-square value has to be above a certain level for us to say, hey, it's different, but this difference is not due to chance. It's kind of confusing because you're looking at it and it's like, oh, it's like 19 and it should be 15, right? So if nothing's going on, we had more people took the real surgery, probably because a lot of clinical trials will have more in the treatment group because we want to give patients treatments, right? So there's more in this group, but by proportion, we should have had 15 and 41. And our expected count, we should have 19 and 36, but we have a lot less having a successful outcome and more having a good outcome in the real group. So it's kind of counterintuitive, right? This should be about 19 and it's less. So you're thinking, oh, it's not the observed, so from the expected, so it should be significant, and we reject the null. But no, we have to do the test to see whether it's significant or not. So with a p-value of 1.4%, who can type in first, yes or no? Yes, significant, no, not significant, with a p-value of 1%, 1.4%. And then I'll come back to Taylor's question. Yeah, this one's significant. Oh no, the corrections are just when our expected counts would fall below 5 or 10. And here you can see they're all above 10. So we wouldn't use a Yates, or is expected, sorry, here's expected. So this one is falling below 10. So this one we would use a slight correction with a Yates correction on this one. So Taylor's asking, when do we apply the corrections? We have to look at the expected counts. If they start falling too low, we can use the correction. So this one we should use a Yates correction for. It'll just adjust this p-value ever so slightly. The reason we do slight corrections in these boxes, and this is why this course is not taught in Coles, the College of Letters and Scientists, a mathematician would say, this value is getting too low, right? That we need to put more people in here, more n's in here. Here's the difference between mathematics and health sciences, nursing, and medicine. Do we want to keep running this test and keep running this trial to have people continue to have bad migraines given the treatment? No, we don't. So we can do a slight correction on this value and still run our test without putting more numbers in here. But a mathematician, if this was a pure statistics course, they'd say, oh, you got to keep running the surgery. You got to keep running the intervention until you get a certain level. We wouldn't do that in medicine. So that's why we heavily emphasize some corrections and we heavily emphasize the chi-square value. So again, what we're doing is we're looking at this p-value, we're calculating, comparing our categories to our test statistic. The chi-square value should be 0, and we're seeing how far that value comes away from 0 when we look at our table. Okay, here's another one that we didn't do last time. We can look at this one. We have, let's go back to StatCrunch. We have 370 subjects assigned to 3 groups. So let's do something with more groups, 3 groups. 120 people took herb1 and 25 got sick. 150 took herb2 and 30 got sick. 100 people took a placebo and 30 got sick. First question, who can type in first? What's our dependent variable, our outcome? The group they were in, what they took, or their sickness? What's our dependent variable here, our outcome, that we want to put in this first column? Yeah, sickness. So we'll just label variable 1 sickness. And again, that's yes or no. We don't have the raw data. So we're going to reconstruct this table. So we've got sick, and we've got herb1, herb2, and placebo. So we gave them some little fake herb that really wasn't an herb, it was a placebo. Oops, placebo. I don't even know if that's the plural. I have to Google that. Okay, so there's our 3 groups. So we're going to have a 3 by 2 table because we've got 3 groups, right? Let's quick do the math here. 370 people. So again, we don't have 370 rows. We don't have the raw data. We're going to put this in. So group 1, 25 got sick, 95, right? Test my math if I'm wrong. Right, 120, yeah, 95, we're okay. 25 got sick, didn't get sick. 95 didn't get sick. herb2, 30. So that leaves us with 120 that did not get sick, right? 100 people, 70 got sick. 70 minus 30 minus 100 is 70. Hope that looks right. So from this one, do the chi-square. Well, again, we go to the stat tab once we get it in. So again, we put our dependent variable in the first row, and then we put our independent variables in the next rows. And now we're going to reconstruct that graph. Tables, contingency with summary. So again, we're going to put in the rows you said with sickness. So we put that there, and we select our ERB1, ERB2, and placebo. Now we're not going to do corrections because those only work for 2x2 tables. See how smart the software is? It's going to tell us what to do. So we can't do that one. So we're going to do a row percent, column percent, percent of total, expected count. We'll click contributions just to see what they are, but you don't have to put them in every time. But you definitely should put in the expected count and the row percentages that we did before. So now it does our table for us. I can just copy this, put it into Word, that one. I'm even going to steal this from up top, and we can just start labeling. So now we've got a 3x2 table because we've got 3 categories. Nominal level variables, both of them, so we can use chi-square. I'm just going to copy this down and then just change them. Again, I'm going to insert a row above. I can merge these and call it group or treatment or whatever I want. That's my columns. Label that sickness. Once I'm done, I can just copy this one down, put a page break in here to square off the table. Again, the total I'll do as well, but I can chop these off because we don't total those up. Backspace, I'm good to go. There we go, there's our table. You know what's coming from a broken record. Yes or no, is this significant? No for not significant with a p-value of 15%, 0.15. Yeah, see, you guys don't need me anymore, you're pros. 3.85, I probably should have did the sig fig so I can just chop them off because 3.85. Again, 2 degrees of freedom because I've got 3 minus 1 is 2 times 2 minus 1 is, so we've got 2 degrees of freedom. Find that table because you know it's coming. Who can be the first to type in? What's our critical value for chi-square with 2 degrees of freedom? What are we going to compare this one to? The test statistic. 5.99. I think my computer's about to die. But I can still see, yes, you guys are right, 5.99. 2 degrees of freedom, there's the chi-square. So again, our test statistic is less than the critical value. It's not significant. We can't reject the null hypothesis. So it doesn't look like the treatment had any effect. Does it make sense? Well, they're about the same, right? So there's a contribution to chi-square. So if everything was null, everything was okay, then we would have this expected count, 27 is 25, 34 and 30, 22 and 30. I mean, it looks like the placebo group got sicker, but it's not significant, right? We don't have the evidence to reject our null hypothesis. Good job. Boy, you guys you're getting better. That's a good sign. You haven't missed a trick tonight. Good job. So there's our table. So that whether we type it in, whether we add it in, we can do the chi-square table. We have this one. Let's look at our homework assignment from week 3. You guys are going to look at this catchment area survey, which is a study from the National Institutes of Mental Health, and it looked at depression levels, smoking, drinking. I think I have that one on my desktop. So again, I'll go over an example from the assignment, but we'll do another analysis as an example, then you guys can do it for the assignment. You'll do smoking. So if we look at this catchment area survey, here the labels are pretty self-explanatory. There's about 100 subjects. We have race, ethnicity, marital status, poverty status, smoking status, BMI, drink status. So this would be how many times they were drunk in the last month, and then how many times they felt down or depressed is what's here. So there's our data file. And let's see, we've got our group. Let's go back to StatCrunch. And this time, let me move this over. So we're going to look at this study, and we're going to look at drinking and depression. So is there a correlation between drinking and depression? So how we feel, how many times we got drunk, or how do we describe our drinking, because this one's a category, compared to the category of our depression, or how we felt down. So to do that, we can load the data in. So this time we're going to have the raw data, right? We'll click load from file. And again, I can just drop and drag this one in. Click upload. And now our Excel file is in there. Again, we click on the stat tab, tables, contingency. Now we click with data, right? Because we've got all the data in there. What's our outcome going to be here? Are we more interested in their depression or the drinking group that they're in? So for drinking, we've got some of the time none. What's our outcome going to be here for a mental health survey? What would our dependent variable be here? Yeah, depression. You guys are pros. So we're going to put that in the rows, right? We've got a lot of choices here. So where did it go? Depression, felt down. We'll put that in the rows, our dependent variable. Our independent variable, we're going to do drinking. How many times they put their category for how drunk they got during that month. So again, in the assignment, you're going to do smoking, but we're going to do drinking as an example. We'll click the row percent, column percent, percent of total expected. We'll leave contributions off since you guys know what that is now. It's not, I don't think it's very exciting to put in a table. We'll put the chi-square in. We can't use the corrections because we're going to have more than a 2x2 table. Even if the counts were low enough, we couldn't use it. We'll click compute. We've got our table. Again, I can copy that, paste it into Word. I think you've seen me type enough about the column and row percents that I probably don't have to do that again. But for sake of time, I won't. But when you do that on your assignments, please do that. It makes the table much easier to read. So there's our table. So quickly, I'll just put the labels in here so we can look at it. So this is our drinking, drunk. How many times they describe being drunk. Again, as a category, because it's just a category, we've got once or twice, never, or 3 or more times. And this is how they felt down or their depression description. So again, we go in here, put percent within counts, right? There's our expected count. But for time's sake, as it goes on, we can see our results. So here we have, again, if nothing's going on, now we had different groups, right? In our totals, we had 36 were in the 3 or more times, 31 and 32. So they're slightly different. So our expected counts are going to be a little different. But here, expected counts 11 and 15. We observed 15, so there seems to be more people feeling depressed the more they drink. If they never did, they didn't end up here. This should have been 9, but we only saw 3. And looking at our score, who can be the first to type in with a 4%, 3.8% p-value, yes, significant, no, not significant for this one, as drinking status relates to depression. Yes, significant, no, not significant. Yes, we've got a lot of votes for yes. Again, below 0.05, this one is significant. You know it's coming next. 10.15 for the chi-square value. Let me make this a little bigger here. I'll move over to the table. 4 degrees of freedom, because we've got a 3x3 table. 2 minus 1 times 2 minus 1 is 4 degrees of freedom. We can be the first to type in what is our value we're comparing the chi-square to at 4 degrees of freedom. Yep, 9.49. And then again, that's our 5% that we made up. Great, you guys are getting it. We've beaten the dead horse, I think. So again, there's our degrees of freedom, and that's the columns minus 1 times the row minus 1. There's our chi-square. When you have nominal level variables, you've just got categories, 2 that you're comparing, and it could be 3 or 2 groups or more groups. That's going to be a chi-square. That's what we're going to do for our test. So again, if you go back to, where's the cheat table? There's the table. So the little cheat area here, these are the ones that we're going to be looking at. So if it's nominal level variables, you're going to be doing a chi-square test. You may adjust it with the Fischers if it's less than 5. like we did, or less than 10, we would do a Yates correction, and possibly a Fischer's if it dropped below 5. Then these other tests are different. So the Mcneimer test, notice it's nominal, but now we've got dependent groups. So when we had our tables we just did, right, these are independent. Either you're in the group that never got drunk that month, or you're in the group that got drunk more than 3 times, or the group that got once or twice. These are separate groups, right? And then the outcome. So the groups are separate, and then are now so nominal, that's a chi-square. But if they're related, then you run this test, the Mcneimer test. Cochrane's Q is for when you've got 3 or more. So it really depends on how many groups you have, what the variables are, and if they're related or not. So for independent groups, if the groups are ordinal level, right, down here, then you're going to have these types of tests, what's called a Mann-Whitney U and a Kruskal-Wallis. And if you go into StatCrunch, I mean, we're not going to do it here, but if you go into StatCrunch and close this one, you'll find those tests here. So there's a goodness of fit, which is we won't do in this class, but here's the non-parametrics. You can find them all here. The only one I really run is sometimes I will put rankings into this test and I'll run a Kruskal-Wallis instead of doing a repeated measures ANOVA. But most of these are not used in nursing and medicine. We stick the chi-square, but sometimes when you have ranked data or you have dependent groups, you're going to use these types of tests. So again, that Mann-Whitney U, it's kind of like an analog of the independent groups t-test. So it tests the hypothesis that the distributions are identical, and there's an even clearer test there. So the Mann-Whitney U is when you have, when you have ordinal level and they're independent. And again, this is in StatCrunch. This would be for when you have ranking. So say these numbers were some kind of rank. We took people and they ranked by body image. So they were ranked, these numbers are rankings rather than just interval ratio measurements. And we can do this test in StatCrunch. These are again for ordinal level variables. Kruskal-Wallis is this one. So it's when you've got, again, ordinal level variables that are independent. Okay, so if it's ranking, you got to use one of these tests. You can't use the chi-square if we're using ordinal measures. So if you've got more groups and you're ranking the data, you can use a Kruskal-Wallis. There's other procedures you can use with Kruskal-Wallis. Once you're done, you can do some other tests on those data as well. For dependent groups, that's when you get into groups that are paired together. These are these tests that are down here. The dependent ones are the Wilcoxon sign ranks test if the outcome is ordinal. So you have to look at that dependent variable. If it's ordinal and the groups are linked, so they're twins or the same people you're measuring again, ordinal, you'd have to use a Wilcoxon sign ranks test, again with 2 groups, ordinal measure. A Friedman if you've got 3 or more. So there's Friedman with 3 or more groups, like ANOVA, right? But with ANOVA, it's interval ratio. With Friedman, it's going to be ordinal and nominal level. So depending on what measure you have is what tests you're going to look at. So again, those are the Mcneimer and Wilcoxon. Those are for these types of tests here, ordinal level data with dependent measurements. So the Friedman, again, is going to be 3 or more dependent groups, like a repeated measures ANOVA. They look similar. So here's the parametric we did last week. So these ones we've actually put into StatCrunch, and we did. This is our independent groups t-test, would be like a Mann-Whitney test, the non-parametric side. A dependent groups t-test is like Wilcoxon signed ranks test. One-way ANOVA, like I said, is like Kruskal-Wallis, so you've got multiple groups. Repeated measures is like a Friedman. So this is from the textbook, page 179, whichever is easier for you to read. This one's probably the easiest. That's where we started tonight, the chi-square, whether we have 3 or more groups or 2 groups, and they're both nominal level variables, you're going to use a chi-square. If it's ranked, you use the Mann-Whitney U for 2 groups. If you use 3 or more groups, it's Kruskal-Wallis. It looks like an ANOVA, right? Mann-Whitney U is like a t-test with 2 groups. 2 groups for nominal level data that are dependent, so they're the same people using categorical variables. You got to do a Mcneimer test, but they have to be related. 3 or more, it's a Cochrane's Q. Then if you have ranked data, it's Wilcoxon sign ranks test. and Friedman test. And again, they're like a pair test or repeated measures ANOVA. So whatever one you want to look at, I look at this one a lot when I'm running tests to make sure I've got the right level variable. Then I look to see if they're dependent or independent groups, and then I pick the right test. But for medicine, the winner is chi-square. If you look at, Polit did this in the chapter, but if you analyze the data for medicine and nursing, you're going to find the winner is chi-square. People put things in chi-square, they tend to have nominal level variables of independent groups because we put patients in a treatment and then we compare them group to group. We try not to use the same subjects or twins or husband and wives and so forth. A little easier, a little shorter this week because we covered most of cross-tabulation in week 1 with all that work we did the first week, right? Making those cross-tabulation tables wasn't that fun. And so we've done a lot of this work already. Let me go back to the course. So the discussion boards, people are already posting up to. So start with the discussion threads, practice your chi-squares, then you can go and work on the assignment. And I think we've covered everything on the assignment. That's all for tonight. Again, this week you're going to have the discussion threads, start there, practice there, work on the assignment. You've got the quiz. Next week we'll meet, we'll do the last part, which is actually review, because next week we've done scatter plots. Then we're going to do regression and correlation next week and do tests on that. So next week we'll sum up with our scatter plots and correlation. So Courtney's asking, for Fischer's test, do you do it just for the cell with an expected count less than 5 or the whole table? If any of them drop below 5, you use the test. So not the whole table doesn't have to be below 5. If any cell in the table drops below 5 for the expected count, you would use the Fischer's. Good question. You're welcome. Okay, I will stop there. And if there's no other questions, I'll stop the recording.